All right. So recall that we looked at this problem last time. We had a line that passed through a point perpendicular to a plane, and we were able to come up with the parametric equations for that line. Okay, and now what we want to do is we want to see in what points does this line intersect the coordinate planes. Okay, so let's go ahead to the parametric equations for the line. We went through this, we went through this solution here, and we found that these were the parametric equations to that line. So just a quick refresher on this. Hold on here. The line passed through the point 513, and 513 is not on that plane. 513 is off the plane because the coordinate 513 does not satisfy the plane equation. 2 times 5 minus 1 plus 3 is not equal to 1. So, I corrected the picture, and the plane has orthogonal, or let me see, it was 510. Thank you. Yep, let me fix that. Thank you. So 510 is not on this plane. Thank you, Ellie. Appreciate it. Because 2 times 5 minus 1 plus 0 is not equal to 1. So you were told that based on the coefficients of x, y, and z in the plane, the coefficients of x, y, and z are 2, -1, and 1. And 2, -1, and 1, if the vector that points in that direction is actually orthogonal to that plane. And we're going to I'll prove that to you later today, a little bit later here. But basically, for this line L, we know that it passes through a point, and we know what the point is, and we know what direction the line goes in. So that's enough information for us to uniquely determine the parametric equations of the line. So using the vector equation for a line, the vector r equals the vector r sub 0 plus t times v. R sub 0 is a point that the line passes through, and the vector v is the direction the line goes in. Based on that, we were able to determine that the parametric equations for the line are x equals 5 plus 2t, y equals 1 minus 1t, and z equals 1t. And we also mentioned that parametric equations for the line are not unique, because these parametric equations here on the right are also parametric equations for the line. That's a yes, because the 4 and the -2 and the 2, the coefficients of t, that the vector 4, -2, 2 is parallel to the vector, the direction vector given by v, 2, -1, and 1. In other words, 4, -2, 2, that vector is equal to 2 times the vector 2, -1, 1. So the direction's the same. So these are also parametric equations on the right. You learned probably, if you remember in pre-calculus, that parametric equations are not unique. All right, but now what we want to do is, yes, Gordon.
No, it's Ned. Or Keanu. My question is that, just to reiterate, sort of the side note that the answer is yes, because both of the normal vectors are proportional to each other?
That's correct. They're multiples of each other.
Okay.
That's right.
Cool.
And therefore they're parallel.
All right. Thank you.
You're welcome. You're welcome. Okay, so now what we want to do is we have these parametric equations, and let's work with the ones on the left here. And given those parametric equations, as t varies, we get different points, and all these points trace out a line in space. Well, we want to know what coordinate this line in space, given by these parametric equations, we want to know, well, like for instance, they say the coordinate planes, right? So like for instance, the XY plane, okay, what point does this line, I mean, this line, I want to be extra clear here. This line given by these parametric equations, is it a vertical line, a horizontal line, or is the line like askew, so to speak? Is this line here, is it vertical, horizontal, or askew, meaning it goes off at an angle in space? Like
It's reflective of the line L, you're saying?
that's right. This
Okay.
line L here, these
Should
parametric
be,
equations, like okay, so we know that line points in the direction 2, -1, 1. We know that line is parallel to this vector here, 2, -1, 1. So could this line be a horizontal line? What do you think? Yes,
We couldn't
yes or no?
not a horizontal line because it has at
Definitely
least,
not.
yeah, one component of X, Y, and Z.
That's right, Mario. Could it be a vertical line?
If we took the dot product between the two vectors, any dot product that was non-zero would indicate it's not. And I think, let's see.
Well, there's only one vector though. There's only one vector.
Oh, okay.
But think of it like this. If you had what's a vector? What's a vector that would represent that would, like, if a line were a vertical line, it would be the direction would be upward, right? So give me a vector. Give me a vector that is like an upward vector. What's an upward vector?
0, 1, 0.
Well, 0, 1, 0 would be a vector. Let's see. I have to think on this.
0, 0, 1, if Z is the vertical component.
That's right.
Oh, yeah.
How about 0, 0, 1?
Yeah.
Yeah, that's a vertical vector, 0, 0, 1. That, matter of fact, that equals the k vector, right?
Yes.
So could our line with these parametric equations, and our line is parallel to 2, -1, 1, could our line be a vertical line? Is 2, -1, 1 a multiple of 0, 0, 1?
No, it's not.
No, so our line's not vertical. Now, like a horizontal line, okay, you could have a horizontal line that goes, like, for instance, in this direction, say 3, -4, and then if it's a horizontal, well, I don't want I there. Let me just, horizontal line. If I wanted my line to be horizontal, okay, then, and I wanted a vector that points in the direction of that horizontal line, obviously there's an infinite number of answers. But what would one vector be? 3, -4, what would the third component have to be? That's right, Ian. It'd have to be 0. Okay, so we can have a horizontal line that goes in the direction of 3, -4, 0. Now, the line that we have that goes in the direction of 2, -1, 1 is our line parallel to this, to a horizontal line?
No.
Definitely not. 2, -1, 1 is not a multiple of 3, -4, 0. So what I'm trying to say here is this line L, this line L traced out by these parametric equations is neither horizontal or neither vertical. Okay, so that means it's going to have to be, you know, going at some angle in space, so to speak. Okay, and it's going to, would it intersect all 3 coordinate planes?
It could.
Yeah, it could, and it does. It actually does. This one actually does, and so, okay, well then, all right, what coordinate would this line with these parametric equations, what coordinate would what point would the line intersect, for instance, the XY plane? Okay, well, how would we find that? If we're interested in the XY plane, okay, that's very good, Ellie. We want to know, I mean, our line would pass through the XY plane when Z equals 0. So if we set Z equals 0, we'll solve for T. And T would equal what when Z equals 0? T would equal 0. Good. So let's go to the next page here. I think we're ready to do this first part here. So the line intersects the XY plane for a value of T that satisfies satisfies these equations. So the key is the Z has to equal 0. And that allows me to solve for T equals 0. And from there, I can get X and Y. And so turns out the line intersects the XY plane at the point 5, 1, 0. Are there any questions on that?
Nope, nothing from me.
Okay, okay. Well, okay, now what's another plane? YZ plane. Now the YZ plane, the YZ plane, all the coordinates on the YZ plane require that the X equals 0, right? In other words, the equation of the YZ plane is X equals 0. So to find where our line passes through the YZ plane, we need to then find a value of T that satisfies these equations here. And it turns out then that we can solve for T based on the fact that 0 must equal 5 plus 2T. So the parameter T would equal -5/2 at that time, at that instant. Okay, so that again, different values of T give you different points on the line. The line moves through space with respect to time, but at that time value, at that T value of -5/2, the line will intersect the YZ plane, and it's going to do it. It's going to do it at the coordinate 0, 7/2, -5/2.
So, Professor, would we describe this as a loss of degree of freedom if we're setting X equal to 0?
Well, it is a loss of degree. Whenever you have a constraint You lose a degree of freedom. And so yes, that's right. That's right. Good, Mario. Good, good. Now you can certainly show that the line L intersects the XC plane at 7, 0, negative 7, 0, 1. I'll let you, you can figure that out. But the XC plane, what's the equation for the XC plane?
Y equals 0.
Y equals 0. That's right, Hunu. So, are there any questions on this in general? Let's move this over. Hold on. Okay. Well, so I want to actually go into the ebook for a moment here and talk about planes. Okay, so give me just one moment. I'll bring up the ebook. Okay, I'm back. Let me go ahead and share the ebook here. Okay, can everybody see the textbook all right here? The word planes? Excellent, excellent. Okay, so lines and planes, planes and lines. Let's talk about planes a little bit. So they mention right in the introduction here, and I'll highlight all this, that although a line in space is determined by a point and a direction, a plane in space is more difficult to describe because a single vector parallel to a plane is not enough to convey the direction of the plane, okay? Because the plane is a two-dimensional entity in three-dimensional space. However, if we had a vector perpendicular to a plane, okay, then that will completely specify the direction of a plane. Okay, so if you, let's see here, one moment. Let me see if I can maybe demonstrate this. Hold on. Okay, so hello everybody. So you see here, I have this. Let me just see. Can I make this? Yeah, I have this plane. Okay, think of this as a plane here, and let me just see. I want something a little bit more, something with a little more density. Hold on. Let me use this. Yeah. One moment. Yeah, here we go. Here's a plane. Now, if I have a vector that's perpendicular to the plane, okay, then the vector determines the plane's direction, because if the vector changes, you know, this orthogonal or perpendicular vector to the plane, if the vector changes, the plane changes. Okay, so the vector perpendicular to the plane specifies the direction that the plane goes in. And naturally, if you have a point on the plane, okay, if you have a point on the plane, that's right, Mario. If, I want to say this the right way, if you have a point on the plane, then that along with the orthogonal vector uniquely determines the plane. So let's go here to a little picture. Let me bring the picture down. Yeah, figure 6. So here in figure 6, you have a plane and you have a vector that's normal to the plane. Okay, and then you have a point on the plane. And together that point, well, you have 2 points on the plane, but the normal vector passes through that point p sub 0, but then you have this other point x, y, z that is another point on the plane, and you can just see that locks down the plane. I mean, if you have, I want to say this the right way. Well, no, I mean, yeah. If you have a point, let me phrase this. Hold on, let me get this back here. Okay. So you see, if you have one point on a plane, the plane can take on a lot of different orientations, okay, and still contain that one point. But if you then include a normal vector to the plane, that uniquely determines the plane. So a point on the plane and a normal vector to the plane uniquely determine the plane. All right, and that's what they're getting at. And based on that idea, you can derive the equation of a plane. Okay, so you look in the diagram there, they've drawn a vector r to the point P, which is a general point on the plane, x, y, z, and then they've drawn a vector r sub 0 to that specific point, x sub 0, y sub 0, z sub 0. So they have the r vector and the r sub 0 vector, and then they've drawn the difference between the r, well, if you take the r vector and subtract the r sub 0 vector, you will get that blue vector, and that blue vector has to lie in the plane, okay, because the points, the terminal points of vectors r and r sub 0 are in the plane. They're on the plane, so the difference of those vectors, r minus r sub 0, that vector is going to lie in the plane. And so that means that the normal vector perpendicular to the plane would be also perpendicular to the r minus r sub 0 vector. Okay, and based on that, you have this statement here. Okay, the dot product of the r minus r sub 0 vector and the normal vector to the plane has to equal 0 because those vectors are perpendicular. Okay, are there any questions on that? Okay, well, can we distribute that normal vector through the dot, like can the dot product be distributed? In other words, what I'm trying to say, maybe I'll show it on the, hold on the whiteboard here. Let me, hold on here. Let me bring this up on the whiteboard. Okay, so normal vector dotted with the r minus r sub 0 vector equals 0. Does it follow that n dot r minus n dot r sub 0 equals 0? Does that follow as well?
Yes, because the dot product is distributive.
That's correct. That's right, Mario and Hunyu. The dot product. That's one of the properties of the dot products, of the dot product. So this means then that n dot r would equal n dot r sub 0. Okay, so certainly this is true. Now the normal vector is some specific vector with components A, B, and C. Okay, with A, B, and C. We'll dot that. Hold on now, I want to make sure. Yeah, we'll dot that with X, Y, and Z. That's the coordinate, that's the terminal point of the R vector in that picture. That's going to equal the dot product of A, B, C with X sub 0, Y sub 0, and Z sub 0. Okay. So AX plus BY plus CZ would equal A times X sub 0 plus B times Y sub 0 plus C times Z sub 0. Okay. Are there any questions on that so far? What I'm trying to do is derive then the equation of the plane, of a plane. So look what we can do. We can subtract the A sub x 0 from both sides, the B times Y sub 0 from both sides, and the C times Z sub 0 from both sides. Okay, and when we do that, we end up getting A times x minus x 0 plus B times Y minus Y sub 0 plus C times Z minus Z sub 0 equals 0. Okay, so this shows this, well, and then, of course, if you wanted, we could write this as AX plus BY. I mean, well, this here is the equation of a plane whose normal vector is given by ABC, those components, and the plane passes through the point x sub 0, y sub 0, z sub 0. But we could write this equation like this. Right? We could write this equation like this. Okay. And that means that, well, AX plus BY plus CZ would equal then A times x0 plus b times y0 plus c times z0, and we could call this whole right side d. So this shows then that we've just proven that ax plus by plus cz equals d would be a simplified version of a plane. The equation of a plane. How many recall seeing this, like maybe in high school or pre-calculus? The equation of a plane, the form of it is given by ax plus by plus cz equals d. Okay, Mario recalls it, Gordon recalls that briefly, and now you know why it's true. Now you know why it's true. You needed to get to multivariable calculus, but you know now why it's true. And I guess the book, what they do is they call this D here. Okay, in other words, I mean, there's nothing wrong with what I wrote here, but if I want to be consistent with the book says AX plus BY plus CZ plus D equals 0. That's how they write the equation of the plane. Okay, so are there any questions on that? All right, well, it's in the recording. Let me get back to the book then. All right, so we've proven then, we've shown that this equation is simply, hold on, let me get to the right thing here. This equation here is simply an equation of a plane through a point P sub 0 with normal vector A, B, C. I mean, that geometrically we showed this, and further, that can be reduced to that equation there, which is one that you've seen before. So this is why in the previous example that we looked at, remember the equation of the plane was 2x minus y plus z equals 0. If I go back to that, let me actually go back to that. Okay, and again, I always have to correct the picture, right? 510 would not be on the plane. Okay, so the plane, the coefficient, I mean, here's the equation of the plane, and the coefficients of x, y, and z were 2, -1, and 1. So 2, -1, and 1 are equal to that A, B, C. Okay, and so that's the vector, that's that normal vector orthogonal to the plane, and that's why you know we were able to say that. So now you have a complete justification. Hold on, I saw a little. Let's see here. Would the equation of the plane, Mario asked, would the equation of the plane hold if the variables were of degree greater than 1? No. Equation of a plane, Mario, the variables x, y, and z are always like to the first power. All right, very good, very good. So now that we understand this, we can do a variety of problems. So Let's look at another example here. Let me give you a moment to copy this example down from section 9.5. All right. Okay, so we have really a very interesting problem here. Very interesting, because we have two planes. Now, just out of curiosity, are these planes parallel? Are the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1, are they parallel?
No.
Or are they not parallel? Okay, why not, Gordon? Why aren't they parallel? That's correct. Those two planes are not parallel.
I don't know if it's the right word, but don't they have to be like proportional to each other? No, is that the right word?
Well, you know, you have a good point there. The normal vectors, and Hyunu is right, but you're on the right track, Gordon. The normal vectors. Hold on, let me get this. Hold on, I don't want any distractions to our lecture here. Let me get this. Let me get this off here. Sorry, class. Let me just. Okay, you get the email off. I don't want any distractions. Okay, so 1, 1, and 1, and 1, -2, and 3. So for the first plane, this is the normal vector. For the second plane, this is the normal vector, and 2. And are these two vectors parallel?
These are also not parallel vectors for
They're-
some reason that Yono said.
That's right. Those are not parallel. And so that means that, you know, the orthogonal vector determines how the plane's oriented in space. Okay, it's how it's oriented. So if you have two normal vectors that are not parallel, in other words, n1 is certainly not, I got to be careful here. I never wrote a not parallel before. Let's see, how would I write that? I guess I would just say n1, that vector is not parallel N1 is not parallel to the vector N2. And so those vectors are not parallel. All right, so, you know, because if we're asking to find the angle between two planes, you know, if the two planes were, let's see here, if they were parallel, then the angle would be 0 degrees, right? I mean, in terms of the, well, actually, hold on. If the two planes were parallel, if they did not these two planes intersect. So that means there's an angle between the two planes at the line of intersection between the two planes. So, but if the planes are not parallel, if the planes are parallel, then this problem wouldn't make sense. So I think we agree the two planes have to intersect on a line, right? Right? These two planes, they have to intersect in a line. And so, you know, well, they intersect in a line, and, you know, the angle there, well, we have to get a little picture here, but hold on, there was a comment here that just came in, one moment. Andrew says take a not equal notation and rotate it 90 degrees for not parallel. Yeah, in order to say that we have an angle between the planes, I guess, you know, Andrew, there's different ways to look at it, but generally, if there's a problem, like in your homework, you know, or on your, you know, exam next Wednesday, you know, that'll be posted next Wednesday, the two planes have to intersect or in order for us to reasonably, that when they say there's an angle between the planes, we're assuming that the two planes intersect. Okay, so good question. Let's look at a picture here. Here's a picture, okay? And, you know, obviously this picture, the two planes in the picture are not the same as the two planes in our problem, because, for instance, in the picture, one of the planes looks horizontal, doesn't it? But the point is, it's just a nice, easy picture. So to help me understand conceptually what's going on. In the picture, there are two planes. Okay, they intersect along a line L. There's an angle theta between those two planes. So same situation with my two planes. They intersect, there's an angle between the two planes. Question is, how do I find the angle? How do I find the angle? All right, well, let me give you a moment to copy the picture down. Okay, let me give you a moment there. And then we'll talk about that. Okay, so what's drawn in the picture here are two normal vectors to, well, you have a normal vector n1 to one of the planes, and you have a normal vector you have a normal vector n1 that's perpendicular to one of the planes, and another normal vector n2 that's perpendicular to the other plane. Okay, and if you were to take so think about now the vectors, those normal vectors n1 and n2, they lie in a plane as well. They lie in a plane. And if we were to take the cross product of n1 and n2, okay, do you see that the cross product of n1 and n2 would go, that the cross product vector of n1 and n2 would have to go in the direction, let me say it this way, the line of intersection, L, would go in the direction of the cross product vector n1 and n1 cross n2. In other words, the vectors n1 and n2, those two normal vectors, lie in a plane. And if you think about taking the cross product of n1 and n2, that cross product vector is going to be perpendicular to the plane that n1 and n2 lie in. Can you intuitively and geometrically see, based on the picture, that the cross product vector of n1 and n2 would have to be parallel to the line L? Does that make sense? I'm trying to justify this comment here. Okay, Andrew's seeing that. Good. Are there any? Because this is central. This is central to us being able to, you know, solve the problem. Because we need the line. We want the line of intersection, right? We want the line of intersection, the line L. And to determine a line L, well, I want to be careful here. I want to be careful. We want to find the angle between the planes, okay? But we're also going to want to find the line of intersection, L, of the two planes, okay? And so, you know, for a line L, we need to know what direction the line L goes in. And turns out that the line L will go in the direction of the cross product of n1 and n2. Okay, but now let's focus on this angle. Okay, so, well, the angle theta here, the angle theta, okay, between the normal vectors m1 and n2 would be, I want to say this the right way. Do you see that the angle theta between the normal vectors n1 and n2 would be the same as the angle theta hold on here. The angle theta between those two planes, do you see that it's the same angle theta between the two normal vectors? In other words, do you see that does that make sense to you? Okay, Hyunwoo makes sense, Elliot makes sense. Kino, it makes sense, okay. And they're using, let me just see here. I'm just trying to see if there's anything, you know, that I can add to that. Let's see here. One moment, class. Yeah, yeah. I mean, it's the fact. I mean, it is a fact that that angle theta between the normal vectors m1 and n2 is the same as the angle theta between the two planes. Okay, and hopefully geometrically you're comfortable with that based on, based on the picture there. So now we have to find, let me know if you have any questions. Now we have to find that theta. Well, the cosine of theta, remember, based on the dot product, the cosine of theta is equal to the dot product of n1 and n2 over the product of their magnitudes. And we know n1 and n2, we know what those vectors are. The vector n1, of course, based on the first plane, the coefficients of x, y, and z in the first plane, n1 will be the vector 1, 1, 1. And the n2 vector, that normal vector, we also call it a perpendicular vector or orthogonal vector. That normal vector to the plane n2, the normal vector, sorry, n2, which is the normal vector to the plane, the second plane, the coefficients of the second plane, the coefficients of x, y, and z for the second plane are are 1, -2, and 3. So they work it out then, and you get 2 over the square root of 42. And so theta is going to equal then the arc cosine of 2 over root 42. And you will get 72 degrees for that, and that is going to be the acute angle. Remember we had the problem where we had two lines that intersected, and the two lines that intersected, there was an acute angle and an obtuse angle, between, well, I want to say it's the right way. Let me phrase it. Oh, it's always, for me, it's always nice to show the geometry. We had a problem where we had two lines. Okay, two lines that intersected. And you have an acute angle between the two lines. That's an angle less than 90 degrees. And then you have an obtuse angle between the lines. That's an angle greater than 90 degrees. In fact, between 180 and 90 degrees. So same thing with the planes. The planes, you're going to have an acute angle between the planes and a obtuse angle between the planes. We happen to get 72 degrees, so that's acute. But if the angle were greater than 90 degrees, if we did this and got an angle greater than 90 degrees, we would just subtract that from 180 degrees to get theta. Okay, are there any questions on this?
Yeah, the dot product, it being positive, that for the 2 in the numerator, that's how we would know that it's acute, right?
That's a good question. Yes, because if the cosine were negative, that means the angle would have to be in the second quadrant. Well, based on your calculator. Your calculator gives angles between 0 and 180 degrees, for instance, using like the arc cosine function. So yes, that's right. That's right, Hyun-Yu, that's right. Square root of 42, let's see, do I have an error here? I don't, let's see, Andrew asks, where's that come from? If you take the square root of 3 and multiply, in the denominator there, square root of 3 times the square root of 14, you get square root of 42. Yeah, that's right, that's right. Okay, are there any other good questions? All right, well, let's move on then. The second question we want to find is the symmetric equations for the line of intersection between the two planes. So again, we make use of the fact that the line of intersection L goes in the direction of the cross product of those two normal vectors. You're welcome, Andrew. You're welcome. And so because of that, the vector v, which is the direction vector for the line, that will end up equaling 5i minus 2j minus 3k. And you can see, you know, when I computed the cross product, I used the technique that the book teaches us. And of course, I would want to see that in your exam work, right? So we know what direction our line goes in. It goes in the direction of the vector 5, -2, and -3. Now what we need to do is find a point on the line of intersection. The line of intersection is the line of intersection between the two planes. And I'm going to give you a moment to catch up here. Let me stop there for a moment. Okay, so again, we know that our line, the direction of our line goes in the direction of this vector v, which is 5i minus 2j minus 3k. But now we need to find a point on that line. And remember what the line is. The line is a line of intersection between the two planes. Okay, so now is this line here, the line goes in the direction of this vector v. Is our line a horizontal line or a vertical line? Or neither? Okay, in other words, is our line askew, or is it horizontal, or is it vertical? It's skew. That's right, Ellie. It's a skew line. So that means that this line has to pass through the xy plane, for instance, at some point. All we have to do is find a point on our line L. The line is a skew line, so SKEW, it's a skew line. So it's going to pass through the xy plane. Well, when it passes through the xy plane, z equals 0. So what we can do is, in both planes, we can set z equals 0, and then find what x and y go with z equals 0. And I do that on the next page. Are there any questions on on the process that we're doing here? Our strategy? Okay. Maybe let me know when we're ready to go to the next page. Okay, Madeline's good. Andrew's good.
Hey, I know that the skew line will pass through the XY plane?
Well, the skew line, let's see here. So the line, if the line were horizontal, then unless it were in the XY plane, let's say it isn't, if the line were horizontal, then it would never pass through the XY plane, right? And we know this line, the fact that we have the -3, okay, for the component, the third component, we know that line is not in the XY plane. Well, now wait, hold on, I got to be careful on that. Hold on. No. Let me take that back. I got to be a little bit careful here because all we know is the direction that the line's going in. But look, the direction that the line's going in, it's not horizontal. Oh yeah, we know that because the third component isn't equal to 0. So this is not a horizontal line. So that means the line has to be going up and down. It isn't like a vertical line either. It's got to be, but it has to be, rising up and rising down, so to speak.
Oh, I
So
think
it's going to pass through that XY plane at some point.
Okay.
Okay, does that make sense? Are you comfortable?
Yeah,
with that?
it's not completely horizontal or vertical, so it's skew, or it's diagonal sort of.
That's correct.
So it will pass the XY plane.
That's right.
Cool.
That's
Thank you.
right. You're welcome. And so we're going to take z equals 0. We're going to find the point where that line passes through the XY plane. And that's going to be the point we're going to use. So certainly z equals 0. And the line is the intersection of the two planes. So it has to satisfy both equations. Any point on that line of intersection has to satisfy the equations of both of the planes. So that means I can take z equals 0 and I can substitute z equals 0 in the first plane and substitute z equals 0 in the second plane. And then I can solve for x and y. Okay, so it turns out that that y equals 0 and x equals 1. So the point 1, 0, 0 lies on this line L. Absolutely amazing. Absolutely amazing. And so now we can get our symmetric equations for our line. Remember, the symmetric equations for a line, any line L. Well, I want to be careful. For this line L, well, here are symmetric equations for a line L in space. We showed those in the last class. So the line of intersection passes through the point 1, 0, and 0. That's our x sub 0, y sub 0, z sub 0. And the line goes in the direction, of the vector 5, -2, and -3. Okay, so that's our A, B, and C. And so here are our symmetric equations. Are there any questions at all? Okay, Juliana's good, and all right. Let me stop this recording.